All right, let's do one more practice problem of repeated eigenvalues using matrix exponentials, this time with an initial condition. So let's solve x prime equals ax with initial condition 1, 2, using matrix exponentials, where a is -3 minus 1, 1 minus 5. So as usual, let's find the eigenvalue here, or eigenvalues. Eigenvalues. So let's do a minus lambda I. So determinant of a minus lambda I. So determinant of -3 minus lambda, -1, 1, -5 minus lambda. Then you evaluate the determinant. So that is -3 minus lambda times -5 minus lambda -1 times 1. And that is 15 plus 3 lambda plus 5 lambda plus lambda squared plus 1. And then you get lambda squared plus 8 lambda plus 16. And that becomes lambda plus 4th squared. And you set this equal to 0, and you end up getting lambda equals -4, which again is repeated. And one question I get very often is, which method do you use when? If you had two distinct eigenvalues, you would do PDP inverse. If you have the repeated eigenvalue, you do this method. So let's find now e to the at. E to the at. So in this case, what you want the e to the a plus 4i to appear. So you see a minus 4i, so a plus 4i. And to make this balanced, you have to do a e minus 4it. Okay. Maybe I'll write it this, e minus 4it. Just like in chemistry, you want to balance the equations. And again, this is the same thing as e to the minus 4t. And for the other term, you use power series. So I plus a plus 4i t. And again, no other terms because of the great fact, that the square of this matrix is 0. So that's it. And we get e to the minus 4t, and then 1, 0, 0, 1. And then we have our matrix, so -3 plus 4, and then -1, and then 1, and then -5 plus 4 times t. So again, the same matrix as for the determinant here. Your -3 minus lambda, -1, 1, -5 minus lambda, but you replace lambda by -4. That's right, you end up getting this. Okay. And then you simplify this, and in the end, you get e minus 4t, and then 1, and then plus 1t. So plus t, 0 minus 1t, so minus t, 0 plus 1t, t, and then 1 minus t. Okay. And then the nice thing is, so I would like to remind you, if you have initial conditions, you do have a nice thing with matrix exponentials, meaning that you can just use those as coefficients. So now let's do initial conditions. Conditions. Remember, x of 0 was, I believe, 1, 2, which tells you directly that x of t now becomes 1 times the first column, so times e to the minus 4t, and then 1 plus t and t, and then plus 2 times the second column. And then e to the minus 4t, and then minus t, and then 1 minus t. So once again, that is the beauty of using matrix exponentials. You can actually use the initial condition as your coefficients. You cannot do that if you do it with eigenvalues, eigenvectors. That's the important difference. And then optional, if you want, you can clean this up a little bit. So this is the same thing as e to the 4t times 1 plus t, and then 1 times t, and then plus 2 times minus t, and then 2 times 1 minus t, which I believe just simplifies to e to the minus 4t, I think 1, and then t minus 2t, so 1 minus t, and then I think the t minus 2t, so minus t, so 2 minus. And the cool thing is, I mean, you can literally read x of 0 equals 1 too, just by plugging in t equals 0.